Okay, so this video is going to be on Unit 9A, which is the intro handout to circles. So let me make the screen bigger here. Okay. So let's take a look at what we got. So the first thing we'll do is we'll just talk about a bunch of terms that come up in this unit. So one of the terms is radius, which you probably already know. If you have a circle, you've got your center point, in this case J, and then anything that goes from the center to the edge of the circle, that segment is called a radius. So a lot of times you'll label it little r or capital R, depending on how you want to do it. And sometimes the word radius is just used to describe how long the segment is. So like if this was 4, you could say the radius is 4, or you could call the radius JK, JI, JL. So if we're talking about the segment for radius, then JL would be one segment, would be one example. So I'll write segment JL, or you could have JK, or you could have JI. You could even draw in other ones, like if I drew JH, that would be another radius right there. By the way, plural is radii. R-A-D-I-I, radii. Okay, so a chord is a segment with both endpoints on the circle. So, like JI is not a chord because only I is on the circle. J is in the circle. So we do have segment MN right here, right? So segment MN is a chord. And then there's another chord right here, LK. Both endpoints are on the circle. So LK is also a chord. So then the diameter, you may have learned already, it's any chord that passes through the center. So it basically starts at one point on the circle, ends at another point on the circle, and it passes through that center point right there every time. So there's only one in this picture, and it's segment LK. A secant is something, this actually comes from Latin, secare, which means to cut. SEC is related to that. You might think of like sections or how you cut up some whole thing, or a sector of a circle is a slice of the circle. Even the word secular, I think, is related. It has something to do with the separation of church and state. So it separates the circle into two chunks. And the formal definition for geometry, it's a line that contains a chord. So here's a chord. This is a line that contains that chord. So line MN is a secant. By the way, informally, you see this all the time. If I draw something like this, that's a segment, like AB, for some reason, a lot of textbooks will still call that a secant, even though it's not really a line that continues on. But if you think about what it does, it cuts right through the circle, all the way through the circle. So I guess that's kind of the informal way of defining a secant. Okay. Tangent, a line in the same plane as the circle that intersects the circle one time. Oh, by the way, tangent, you might have heard the word going, like the phrase going off on a tangent. That means that you have your topic and then you kind of found something related to your topic, but just barely related, and it just kind of grazes the topic, and then you go off in some other direction. So that's related to the tangent for a circle. It's a line that is close to the circle, just barely grazes the circle, and then kind of goes off in its own direction there. So HG would be a tangent line. By the way, the word tangent, you might have heard tangible. That has to do with touching. And so a tangent line is something that just touches the circle, but only at one point. So the line here is HG. So line HG. And then the point of tangency is where the tangent line hits the circle. So in this case, it's point H. By the way, if I drew a segment that only hits at the circle one point, And if you kept it going, it would be tangent. You also call that segment a tangent line too. So like AB here, that would be a tangent. But not this one, right? That like CD, not a tangent. Because if I kept CD going, it would cut right through the circle. So that's definitely not a tangent. It would have to just graze even if you kept it going. Okay. Minor arc. So that's an arc, a part of the circle that's less than 180 degrees. So less than half the circle. So a minor arc, let me erase this stuff. So a minor arc would be like HL, that arc, or HM, that arc, or MN, that arc, or H to K, that arc. So any arc that's less than half of the circle, right? So the way that you do that, you denote two letters. So like, what's one of them? HL, let's say. So HL. And then so that you know you're not talking about like a segment that connects H to L, because if I just wrote HL, a lot of people would think that's segment. So you could either put arc in front of it. You can say arc HL or minor arc HL, or you can put a little arc symbol above it. So HL would be one. We also said HK, that would be one. IK is one, NK is one. So there are a bunch of them. IK, what did I say? NK, etc. A major arc is an arc that takes up more than 180 degrees. So for example, let's say I started at L and wanted to go all the way around to K. That would be half the circle, and then a little bit more, so that I ended up at I there. So that would go start at L, end at I. And in order, if I just wrote LI, if I wrote this, then that means the smaller one. So if I want to denote the bigger one, I throw in a letter in the middle, one of the letters that I pass along the way. Any of them, like LMI or LNI or LKI. So an example would be like LKI. Use three letters, that means it's more than half the circle. Another example, like let's say I started with K and I wanted to go all the way around to N, right? Well, I can't call it KN because if I call it KN, I'm talking about the small one. So I'll do KHN or KLN or KMN. Right, something like that. Oops, wrong place. And then if I'm talking about a semicircle is exactly half so of the circle. So like I'd either pick this half of the circle or I'd pick this half of the circle. And you can't use two letters because then you don't know which half you're talking about. So you throw in one middle letter. So like if I'm doing this one in blue here, I can say like LHK, for example. LHK. And if I'm talking about the one in, here I'll highlight it in red. So if I'm talking about this one in red, I could start with like L and then M and then K or LNK. Something like that. Okay, so those are a lot of the terms. And then there are a couple other terms that come up throughout the unit. One is called concentric circles. So co is related to sharing. Centric, if you kind of think about a word that sounds like that, would be center. So this is circles that share a center. So here's a center point, and here's a circle, and there's a circle, and there's a circle. They don't have to be evenly spaced out. Like this one could be closer, right? But as long as these are all supposed to be circles with that center point, these would all be concentric circles. Basically looks kind of like a target symbol. And then there's this thing called inscribed and circumscribed. So in just means inside and scribe means to write. So it's a polygon that's written inside something. Circum means around, like if you've heard of circumnavigate the globe, that means travel all the way around the globe. So around and right. So a circle that's circumscribed is one that's written around something else. So if I draw a circle and then I put some shape inside of it, now it can't just be a shape floating around inside. That's not technically inscribed. But if I did something like this, where I put all the corners of the shape on the circle, and it doesn't really matter how many corners it has. So let's say I did this. Then this thing, the polygon in the inside, it's a pentagon. It's an inscribed pentagon. And the circle is written around it, so it's a circumscribed circle. Okay. So let's do some problems here. All right, so there's a theorem that says if you have a tangent line, then the tangent is perpendicular to the radius drawn to the point of tangency. Now that sounds more complicated than it is. Basically, it's saying if you have a wheel, like think of it like you have a bunch of a bike wheel, and you've got all these spokes. One of the spokes is perpendicular to the ground. That's the one that comes straight down to the ground. And if you think about it, the ground is a tangent here, right? Whoops, undo. This is tangent right here. So the radius drawn to the tangent is going to form a right angle. And now you don't always see it written like this. A lot of times you'll have a problem that looks like this instead, and you have to realize if that's a radius and this is a tangent, that's a right angle. Okay, so let's read these problems. So JT, this guy, is tangent to the circle O. You say circle O if O is the center. Circle O at point T. By the way, some books will denote circle O like that. The first part means circle, and then the center point goes there. So like it could be circle P or circle X. Okay, so it's tangent at point T, which means these form a right angle. OT is 6, JK is 4. How long is JT? So we'll call JT X. Okay, well I can't do Pythag yet, because I only know one side. But notice that this one side is the radius. Well, this is also a radius. So this also equals 6, which means if I draw the triangle by itself, this part's x, this part's 6, and this part is 4 plus 6, which is 10. So now I can do Pythag. 6 squared plus x squared equals 10 squared. And if you work that out, you'll get x is 8 and x is JT. So we get 8. Okay. Part B, it says try the same problem again, but now suppose that this guy's 2, this guy's 4, and we're supposed to assume that this is still a tangent with a radius, so we get the right angle. Okay, well I can't do anything yet, but I do know that I have a radius right here, and I have a radius right here. So if I draw this triangle by itself, I've got 4 down here, radius there, and 2 plus a radius here. We want OT, which is this side, so really I just want R. So if I set up Pythag, I've got R squared plus 4 squared equals R plus 2 squared. So if I work this out, R squared plus 4 squared, oh, sorry, it's covering up the mic. I hope that didn't mess you up too much. Equals think of this as R plus 2 times R plus 2, so I'll write that out. So R squared plus 16 equals R squared plus 2R plus another 2R plus 2 times 2 is 4. And then if I get, well actually, the R squareds cancel. So if I bring this 4 over, I get 12 equals 4R. R equals 3, which is the same thing as OT. So OT equals 3. Okay, in the next problem, number 2, I don't know why these arc symbols got shifted over. They should really be on top of CB there. Well, I guess that's the only one that got shifted. Okay, so there's this theorem here that says the measure of a central angle in a circle is equal to the measure of its intercepted arc. So a central angle is an angle that comes out of the center of the circle. We've actually talked about this briefly in class, but whatever angle this is, that central angle, intercepted arc means the arc that it kind of carves out in the circle. So if this angle was like 40 degrees, this arc I could also call 40 degrees. And if you think about it, if I go all the way around the other part of the circle, it's 360 total. So this would be 320 degrees, which means its arc right here, you could say its measurement is 320 degrees. So let's see what we got in the problem. The arc CB, so this arc is 60 degrees. And CAD, so this angle here, is 52 degrees. So then we got to find all these other arcs and angles here. So let's see what we got. BDA. Oh, and P is the center of the circle. P is the center of the circle. So if I go from B to D to A, right there. Well, notice if P is the center of the circle, BA is a diameter that cuts right through the center. So that actually means that this is half a circle up on top. So this is 180 degrees. 180. Okay, let's see. What else do we need here? Why don't we just fill in whatever we can first? So let's see. I know that this arc is 60 BC. So that means that this angle right here, the central angle has to be 60. Let me get rid of this. I know that the angle next to the 60 right here, that has to add up to 180 because this is a straight angle. So the angle next to it's going to be 120. So I'll put 120 right here. Okay, so here's where a super important idea for these problems comes in. If you notice, this line and this line right here, those are radii. In fact, so is this one here and this one here. So all of those yellow segments are going to be the same length. Right? These are all congruent to each other. So if you look at CPA, that triangle there, it's isosceles because these are both radii. And this was 120. These angles would have to be the same. So if I do 180 minus 120, I get 60. And then if I cut that in half, I get 30 for each of these angles. 30 here, 30 there. 30 here, 30 there. And then I know this whole angle on the right side is 52. So the leftover is 22 degrees. Oops. So this one here is 22 degrees. Let's see. Okay, so then if I look at this triangle, that one's an isosceles triangle because of the radius and radius. This one is DPA. Let me get rid of this picture. Okay, so we knew that this one was 22, which means this one has to be 22. So if I do 180 minus 2 times 22, I'll get 180 minus 44, which is 136. So that's this central angle right here, 136. And then that means that the angle next to it, if I subtract from 180, 180 minus 136 will be 44. So this arc is 44. Or sorry, that angle is 44. So let's see, we've got pretty much all the little angles in the triangles now and the central angles. So that's the key to the problem. So let's see, we've got 180, BD, BD. That's this arc. That's going to be the same as its central angle. So that arc's 44 degrees. Let's see, where's COD? COD. Oh, that's a misprint. That should say CPD. Sorry. So CPD is this angle here, which is 60 plus 44. So 60 plus 44, that's going to be 104. Arc CD is this arc. Well, since its central angle is 104, this arc is 104. And then BDC. So BDC, 3 letters. It's either half a circle or a major arc. So start at B, go around to D, and then keep going until you get to C. Well, you could add up all the central angles that go around there. Or you could say, I know the whole circle's 360, and the part that I didn't include was 60. So the leftover is 300. Okay, so let's go on to the next part here. So number 2, it mentions that central angle, whatever this angle is, if I call that x, this arc is also x degrees. Sorry about the construction noise if you hear that, and the crows. Okay, so there's another type of angle that we're going to study with circles called an inscribed angle. So that's one where the angle is on the circle, and then you've got chords that come out of it. And so the question is, how does this angle compare to this arc? It's not central anymore. It's not coming out of the center of the circle, so it's not necessarily the same size. But if we go back to number 2, we've got some examples to look at. So let's highlight a few of these. So here, like here's an inscribed angle right there, and the arc that it carves out. So if I draw that by itself, this angle is 30, and this arc is 60. And there's another one that we've got to look at, like this going up to here. So that whole angle was 52, and this arc is 104. So if I draw that one, let's see. This isn't great diagramming, but 104 here, 52 there. So you ought to be able to get a pretty good sense that, well, if I take the inscribed angle and double it, I get the arc. Inscribed angle and double it, I get the arc. Or take the arc and halve it, and you get the angle. So whatever this is, this one's double it. So the inscribed angle equals half of its intercepted arc. Or the intercepted arc equals 2 times the inscribed angle. Okay, so that one will come in handy for some future problems. All right, so let's take a look at 4. And again, I don't know why this angle symbol got, or the arc symbol got moved over, but these guys should be over the letters. Okay, so P is the center. Chord AB is 2 centimeters from P. So the way we draw that in is you want to draw the shortest segment possible and say that's 2 centimeters. And if it's the shortest distance, then it's got to form right angles. So that's useful. Radius is 5. I could draw a bunch of different radii, but the ones that tend to come in handy are the ones that go to points already on this circle. Like that one's 5, and that one is 5. Let's see, find the length of chord AB. Well, this shouldn't be too bad if I do Pythag. I've got 2 squared plus x squared equals 5 squared. So let's see, that's 4 plus x squared equals 25. So x squared is 21, and then you take the square root. And that's 3 times 7, so that doesn't reduce. And I've got 2 of them. So AB is really 2x. So it's 2 times root 21. 2 root 21. Okay. The next one says, what's the measurement of this arc? Well, the measurement of that arc is the same as the central angle that carves it out. So let's see here. If I call, how am I going to do this? It's so tiny. let me draw this triangle by itself again. So here's APB. Really what I want is this angle. It's a central angle, so it's equal to this arc right here. So that's this angle. And I already know that this is 2, these are 5. And since it's isosceles, if I chop it down the middle, this angle and this angle are going to be the same. So I'll call them theta. And if I just look at one of those triangles, 2, 5, and theta, I'm going to have to use inverse trig. The 2 is the adjacent side. The 5 is the hypotenuse. So we'll use cosine. So cosine of theta is 2 over 5. So theta, I'll have to use cos inverse to get the angle. Theta ends up being about, let's see here, cos inverse of 2 over 5, it's about 66.4218 degrees. And then I have to double it because there's 2 of them. So that's about 132.844 degrees. And notice that the arc here, that's going to be the same as the central angle. So arc AB is going to be 132.844 degrees. Okay, the other question is, what's ACB? What's this angle? So here's A to C to B, right there. Whoop, oh geez. So we're looking for this angle. Now if I draw that angle by itself in the circle, ACB, we just figured out that this arc was 132.844 degrees. Well, this is an inscribed angle, so it's going to be half of the arc that it carves out. So that means I need half of 132.844. But we already have that because we just doubled the number 66.4218 to get the 132. So if I have it, I get 66.422 degrees. Okay. Let's see. Number 5. All right. So this looks complicated, but it's not terrible, actually. So let's fill in what we know. SR is tangent to both circle P and circle Q. So that means any radius so this line right here is tangent, which means the radius PS is going to be perpendicular, and the radius QT is going to be perpendicular. Okay, let's see, what do we know here? TR is 8, QT is 6, PR, this whole length, is 30. All right, so let's see, we need PQ, PS, and ST. All right, so let's see what we can figure out. Let me draw these by themselves, the triangles by themselves. So right angle there, right angle here. This was 8, this was 6, this is 30. Now we've done a ton of problems like these where I've got a triangle chopped with another line here, and because these angles, these corresponding angles are congruent, I know that these lines are parallel. I've got a reflexive angle right here. I've got similar triangles. The big one and the little one are similar. So if I draw the big one by itself, here it is. Let's see, the letters are S, P, R, where this is 30. And then the little one looks like this, 6, 8, unknown. And let's see, it's T, Q, R. Okay, well, I can solve for QR, right? Because QR is just the hypotenuse of a right triangle. So if I call that, I'll call that x. So I got 6 squared plus 8 squared equals x squared. And if you work that out, you get x equals 10. So now I can set up proportions. Right? So I can say, like, if I call this y and z, then I know that y over 6, this side over this side, is the same as 30 over 10. So if I cross multiply, 10y equals 180, y equals 18. So this is 18. Right there. This part's 10. Let's see. I can also set up 30 over 10 is the same as z over 8. So then I got 240 equals 10z. So z equals 24. So let's see. That's this whole thing right here. 24. So what do we need? We need PQ. If the whole thing's 30, this part's 10, PQ is going to have to be 20. PS we already have is 18. And then ST, if the whole thing's 24 and this part's 8, then this part's 24 minus 8, which is 16. Yeah, okay. All right, let's see what else we got here. Okay, so let's take a look at number 6, which deals with rotation problems. 6 and 7. So let's see, 6. We got a 90-degree counterclockwise rotation centered at this point, 4, -2. And it's applied to the point -1, -5. So this is a 90-degree rotation right here. Now, you might remember the rule xy turns into -yx as the 90-degree counterclockwise rotation, but that's if the center is the origin, which this one is not, right? The center is 4, -2. So you can do a couple things. You could move this to 0, 0, and then move this one to wherever it would end up, then rotate it, and then move everything back. But I think that it might be easier if you think in terms of the slopes. So if we look at these two segments right here, you know that the central angle here has to be 90. So this slope and this slope have to be negative reciprocals from each other. So if I were to draw in a slope triangle right here, I can calculate that one because I know the endpoints. So let's see, when I go up and down, the y's change from -5. Oh, sorry, that's a misprint. That should be a 2, not a -2. +2. So -5 to +2, that's 7 up. And then 1 to 4, that's 5 across. So this guy's slope is 7 over 5, which means this guy's slope better be -5 over 7. So if I start at this point, my rise is 5 down, and my run is 7 across, and then I just need to start at the point 4, 2. Whoop. Start at the point 4, 2. Whoop. And say, well, let me go 7 across and 5 down. So here's 4, 2. I'm just redoing it on the side here. 4, 2, 7 across, 5 down. That gets me to A prime. So 7 across turns the 4 into an 11. And the 5 down turns the 2 into a -3. So we get the point 11, -3. Okay, let's take a look at 7. So in this one, we're centered at the origin, but it's not a 90-degree rotation. It's now an 80-degree rotation. So let me draw in this radius and that radius. And you can kind of picture if I kept this thing going, it would form this gigantic circle around everything. So we know that the radii are the same. So this is, I'll call this capital R for radius. And the central angle here is going to be 80 degrees. So let's see, what can we figure out? We know that this is 0, 0. And we can calculate how long the radius is, which will help us get this other R over here. So if I do that, I'll build a little slope triangle. And since I'm starting at 0, 0 and going to 3, 8, I know it's 3 over and 8 up. And so I can do 3 squared plus 8 squared equals R squared squared. So that's going to be 9 plus 64 equals R squared. R is going to be root 73. So this right here is root 73, and this right here is root 73. Okay, now if I knew this angle right here, then I could use trig on the triangle over here on the left, this blue triangle. I could use trig on it to figure out how far over and how far up I have to go. In order to get that angle, I'm actually going to solve for this angle in the red triangle. So I'm going to call that, I don't know, we'll call that alpha. So I'll use the 8 and the 3 to get the angle instead of the root 73. You could use root 73, but 8 and 3 are nicer numbers. This side's the opposite side. This side's the adjacent side. So tangent is the trig ratio that I'll use. So tan of alpha, tan of my angle, equals opposite over adjacent. So alpha is going to be the inverse tangent of 8 over 3. And then I'll plug that into a calculator here. So clear that. Tan inverse of 8 over 3. Oh, sorry, I got to switch modes. Degree mode. And then I'll just hit enter again. So it's 69.444 degrees, roughly. So that's this angle down here. So let me mark that up. So this one is I'll use a different color. 69.444 degrees, approximately. So then this one, I'll call this one theta. So theta is going to be 180 minus 80 plus the 69.444. So that's going to be 180 minus the 80 plus that 69.4 angle. And we get 30.556 degrees. So that's this one. Okay. So now what I need to do is I need to solve for this length over here and this length over here. So I'll call these, I don't know, we'll call them A and B. Right? So really what I'm looking at is this problem here. A, B, theta is 30.556 degrees, and this is root 73. And so if I wanted to solve for A, I'll call this side the adjacent side. This is the hypotenuse. So adjacent and hypotenuse is cosine. So cos of my angle, 30.556, equals A over root 73, adjacent over hypotenuse. And then if I multiply the root 73 over, I get A. And let's see here. So it's root 73, and then I got to get out from the root, so I hit right, times cosine of that 30.555 angle. So I'm going to cut and paste that, and hit enter, and we get 7.3575 for A. So this is 7.3575-ish right there. And to get B, that's the opposite side. So I'm going to use B and the root 73 with this angle. So that uses sine. So sine of theta, or sorry, 30.556 equals B over root 73. So I got root 73 sine of that angle that I can cut and paste because it's a long decimal. And B ends up being root 73, move the cursor over, times sine of that 30-degree angle. And we get 4.3436. So this one is 4.3436. So then the last step is, where is A prime located? Well, I started at 0, 0, and I went 7 units this way and 4 units up. If I go 7 units backwards, I'm in the negative. So it's negative 7.35, let's say 8-ish if I round up. And then when I go up, the y's become positive, so 4.345. Okay, I hope that helps a little bit, and I'll see you guys soon.